Okay, so good morning. This lesson is taken by Shanker's principle of quantum mechanics, and in the specific, we can say that we are able to consider the path integral evaluation of the free particle propagator. Okay, we start from Feynman's assumption that utility the propagator is equal to a coefficient A, E, action classic, S classic on H. Okay, we can suppose we calculate x classic, the position classically with the classical procedure, and we go to S classic with the classical procedure by the integrals. Okay, and so we can calculate the result, that is there is equal to m, and you can read it. Okay, the objective of this video is to evaluate not an approximation but a calculation, formal calculation of this result. Okay, we start by considering the integral between x0 and xn, find the point, interpoint of a e s xt on h, integrate over all possible, integrate, I said, over all, again, I can't do it letter, d is a differential over all possible paths. This means that we want to integrate over all possible paths connecting x0, xn, all these infinite possible paths. Is a notation, okay? Is a notation. So let's start. A path is fully specified by an infinity of numbers, xt0, xt, xtn, namely the values of the function xt at every point of the interval. Okay, so we can replace the continuous path definition as L de Lagrange t equal to t0 tn 1 on 2 by the discretized action. So it's obvious that we are arranging a discourse that affords us to take the limit on infinity. So S is equal to summation is equal to 0 and minus 1 and on 2 x equals 1 xc on epsilon, where epsilon is the time interval infinitesimal, and dt obvious epsilon dt, we suppose. And this is the action discretized. You write discretized action. Okay, now we can impostate the intervals u, xn, tn, t0, t0 equal to integrals 0, xn, exponential e s xt on h, the xt. And this is with some easy on notation, lim on n to tend to infinity, epsilon to tend to 0, are integrals infinite plus infinite, infinite plus infinite, plus infinite, x dE on h, and 2 on 2 e equal to 0 and minus 1 xc plus 1 minus xc on epsilon 2 squared. Okay, we have, I forget the differential, the x1 still takes n minus 1 because we start from 1. Okay, we can change the variable. Change the variable epsilon e is equal to n to h epsilon 1 to x. Changing variable. We obtain that lim n tend to infinity. Go back in the video. Infinite, infinite. Why minus infinite plus infinite? Because we have to integrate over the path that are all the space, all the manifold. Infinite x the main summation 0 and plus 1 epsilon equals 1 on 2 on e the epsilon 1 till the epsilon and minus 1, where a primo right is equal to a 2 h epsilon minus 1 on 2. Perfect. Well, so we are ready to calculate these integrals. That seems to be an effort, extraordinary effort, but it's simple because integrals means infinite plus infinite x on e epsilon 2 minus epsilon 1 second plus epsilon 1 epsilon 0 on 2 the epsilon 1 to integrate only this is equal to, perform the calculation left as exercise, e pi greco on 2 e epsilon 2 minus epsilon 0 2 on 2e. Okay? Consider next the integration over epsilon 2. The integration over epsilon 2 is e pi greco taking the result just calculated on 2 infinito, infinito e alla meno y3 meno y2 square on i perché meno y2 meno y0 on 2 2e the y2 and this sorry for some passage on 3 second. E meno y3 y0 2 on 3e. So comparing this result to one from the y1 integration, we deduce all. What is this all? That p great alla n meno 1 on 2 is equal min y n y0 2 on n. Sorry, I am a little bit disordered. On n. So bringing in the factor, u is equal to a and so we are arrived to the previous result. Okay, bye bye.